All right, in the previous video, I went over a little bit of the beginnings of what is called the Dirac notation, which is also sometimes called the Bra-Ket notation. And so that is essentially the same thing as linear algebra, except we're using these bras and kets. And so if we had something like say this, then that was equal to the complex conjugate of A multiplied or dot product or inner product with the with A, and so we could write that as our row vector. So we put the star there to tell us that that is the complex conjugate A star 2, A star 3, and so on. It could keep going, but I'll just do 3 dimensions here, then multiplied by our vector, our ket vector. So that's A1, A2, A3 in this column form. And we saw that that ended up being equal to A star 1 times A1 plus A star 2 times A2 plus A star 3 times A3, and that was all equal to a scalar, and so that was the dot product of that. And we also saw that we could do scalar products, so we could have alpha multiplied by A, and you can do it the other way around too. You can have A multiplied by alpha. And so this is, as I said, what we covered in the previous video. So in this video, what I'm going to start with is we can also have, just like in linear algebra, we can multiply these ket vectors and bra vectors by matrices. And so if we have a matrix M multiplied by A, this will perform some transformation on this ket vector. And then we can also call this, well, and maybe the mathematicians will scream at me for this, but we can call these operators, and in future videos I will get more into what operators are. But for now, we'll just call this a matrix, and so we are using a matrix, and it's called an operator because it's operating on this ket, and that will give us some other ket. And so just like when in linear algebra, because I mean that's pretty much what we're doing here with the Dirac notation, we're just doing it a little bit differently, in ways that are helpful for doing quantum mechanics. It's not just sort of an aesthetic change here. There is a reason for doing it this way. But like I said, it's pretty much just doing linear algebra, and so we can take this matrix and we can give it elements, and so I'll call the matrix, so I will call it Mij, and these are telling us what the elements are. And so this will be a matrix, so our first element will be M11, then we'll have M12 and M13, and so that is our first row. And then we just keep cycling through these elements, these indices here, M22, M23. Then the bottom, the first number on all of them will be 3, M3, M32, and M33. And so the first thing you will notice is on the diagonal here is when I and J are all equal to each other, and that it will be important to remember. But what we have here, like I said, is just sort of a general matrix, and the matrix multiplication with a vector will be pretty much well, it will be done exactly the same way. Uh, so I'll use a smaller matrix just to keep things simpler. So if we have m times a, we could say that that is m11, m12, m21, m22, multiplied by our vector at a1 and a2, and this will give us m11 a1 plus m12 a2. So that was m11 times our a1 plus m12 times a2. So it's always first, first, second, second, but in the matrix we are going by row, and in the column vector obviously going by column. And so then we know that the bottom will be m21 times a1 plus m22 times a2. And this will be our new vector here. And so we could maybe simplify that and call this up here what this will be equal to as b1, and this down here will be equal to b2, and so that is our new vector there. And just as in, if you've watched my linear algebra videos, what this matrix is actually doing, so these diagonal elements here, so that would be these ones here, are scaling elements. So these are scaling. If we have a vector like this and everything not on the diagonal is 0, then all we're doing to our vector is, well, we could either keep it exactly the same if everything equals 1. If they are larger than 1, then we would increase the length of the vector, but we are not changing the direction it's facing. And if they are less than 1, then we would be making it smaller. Whereas the off diagonals are telling us which way to rotate this vector. And so this is essentially telling us how much we want to move our first component in the direction of the second component. And so it's essentially saying, so I will scroll down here, and if we have this vector here, like I said, this element here would be telling us how much to scale it in one direction, and this one would be telling us how much to rotate it. And so this is telling us how much we want to change our x direction, our x component in the y direction. This is telling us how much to change our x component in the x direction. And so if we want to change our x component, which is this, in the y direction, then we would have to move it that way. And so that is telling us what to do as far as a rotation. All right, and so other things important to understand about matrices is if we have our matrix, which is I, J here, then we can take the what's called the transpose of it. So we put a T up there, is I, J, which will equal M, J, I. And essentially what that is doing is we are taking our components. So if we have M11, M12, M13, M21, M22, M23, then M31, M32, M33. So we have this as our matrix. Now, if we want to take the transpose of that, then these diagonal elements will remain where they are, but all of the other ones will be switched around with sort of their corresponding ones. So these will all be switched around. So what we end up with is M11, M 2, 1. So this one was moved up here. Then M3, 1. This one here was moved up there. Then we have our M1, 2. So this one right here was moved down there. M2, 2. The diagonals stay the same. Then we have our M3, 2. And so this one right here was moved up to right there. Then we have our M1, 3. And so this right here was moved down to there, our M2, 3. And so this one right here was moved down to this right here, and then M3, 3. And that is the transpose of the matrix. And then another thing we can do, so if our matrix has elements that are complex numbers, then we can actually also take the complex conjugate of our matrix. And so, well, I'll keep this one smaller. So if we have our M11, M12, M21, M22, if we say that these are complex numbers, so maybe we could say that this is essentially like 1, then 1 plus I, 1 minus I, and 1. And we are taking the complex conjugate of these. So this is so take the complex conjugate of that. Then what we end up with is 1, 1 minus I, 1 plus I, and 1. And so we see that the sign on these change. And so we can do this as well with, if we have, we can take the complex transpose of a matrix. So if we have M11, M12, M21, M22, and we say that these are complex numbers, so if we have 1, 1 plus I, 1 minus I, and 1, now if we take the complex transpose of that, which is often shown as this thing called a dagger. And so what we would do is well, we can do this sort of stepwise, I guess. So the first thing we do is we take the transpose. So we take the transpose, which would be 1 minus I, 1 plus I, 1. So that is the transpose. Like I said, I'm doing these sort of as a sequence. This dagger tells you that you're sort of doing it all at once. But if we do this sort of sequentially here, so then after we take the transpose, then we do the complex conjugate, and now what we end up with is exactly what we had before, which is the 1, 1 plus I, which is what we had here, 1 minus I, which is what we had here, and 1. And all of the elements could be complex as well, but I am showing it like this here sort of suggestively, because what we have here is what is called a Hermitian matrix. Hermitian. And a Hermitian matrix is one where it's complex. It's the complex conjugate of the transpose just recapitulates the matrix again. So you just get the same matrix back out after you do the transpose and complex conjugate. And so what we could say is that that if this is Hermitian, in fact, I will switch to calling it H, and we have IJ here, and we take the complex conjugate of it, we will just end up with HIJ again. And so that's what a Hermitian matrix is one that has this property here, that the complex conjugate of the transpose is the same matrix again. And that will be important to remember later on. And I've already sort of touched on it before. If we have a matrix where we have one as the diagonals in the matrix, then we are not when we act on a vector with it. So if we have A1, A2, A3, then we just get our vector back again, A1, A2, A3. We're not scaling it or rotating it at all. And this is what is called the identity matrix. And so if we have I times our ket vector, we will just get our ket vector back out. And so this goes back to what I was saying before up here, where if it's just the diagonals, then it's just a scaling. But if the diagonals are 1, then we are just staying at the same length here. And then if all of the off diagonals are 0, then we are not rotating in either direction. It is just staying where it is, and that is what the idea, what the identity matrix is. And so one other, well, actually I have two other things to talk about here. The first one is what is called the determinant of the matrix. The word escaped me there for a minute. Determinant of the matrix. And so, well, I'll start out with just how to calculate this, and then I'll talk a little bit about what it means. So it's calculated differently depending on the dimensionality of the matrix. So it's often written like this. So we have the determinant of some matrix M, and if the determinant of the matrix M is a two-dimensional matrix, we have A, B, C, D, and you will often see it written like that. Then the determinant will be A times D, so this times this, minus B times C, so minus that times that. And as I said, this is a two-dimensional matrix here. And so the way to interpret that is that we are essentially taking the area inside this parallelogram here. And so we can say that AB, so AB is one side of the parallelogram and CD is another side. And the determinant tells us essentially whether the area of this is well, it tells us the area, and if it equals 1, then using this matrix on a vector is not changing sort of the magnitude of that vector. Whereas if this was going to be greater than 1, then you are sort of increasing, so you might be changing its direction, but you're also increasing the magnitude. And if it is less than 1, then it's reducing that magnitude. And so this essentially tells you something about the way that this matrix will transform a vector. And so that will be, that's an important thing to understand about the determinant. And you can also do the determinant in 3 dimensions. And for that, if we have the determinant of the matrix in 3 dimensions, that will give us something like A, B, C, D, E, F, G, H, I. And so we will have that. And what we do here is we first take A, E, I, so that that diagonal A times E times I. Then we sort of move over 1 and take the diagonal, so that diagonal goes from here to here, and then this sort of goes down to here. So it'll be BF, or no, sorry, it should go down to here. So it'll be BF G, and then we do the same thing. We go from C down to D, then down to H. So C, D, H. And then we subtract, sort of going in the opposite direction. So it'll be CEG, CEG plus, and then we, just like before, we move over, we go B down to D, and then down to I, so B, D, I, and then we move over again, so we have A down to F, down to H, so A, F, H. And this gives us the determinant in 3 dimensions, which is the area of this, what's called a parallelepiped. And so I actually got these from Wikipedia, which we can look at here. So this describes it as, so this right here says the area of the parallelogram is the absolute value of the determinant of the matrix formed by the vectors representing the parallelogram sides. And sort of the same thing if we're in 3 dimensions, the volume of this parallelepiped is the absolute value of the determinant of the matrix formed by the columns constructed from the vectors R1, R2, R3. So R1, R2, R3. And so, like I said, that just tells you a little something about how this matrix will transform your vectors. And so the last thing I wanted to talk about here about the matrices is what is called the trace of the matrix. And so that is often written like this. So trace of the matrix. And that is just adding up the diagonal. So if we have A, B, C, D, then the trace of this will just be A plus D. And if we have A, B, C, D, E, F, G, H, I, then the trace of this will just be A plus E plus I. So it's just adding up the diagonal here. And that also tells you something essentially about how this matrix will scale your vector, because as I said, the diagonals are sort of the scaling factors here in the matrix. And so that is, I think that's all I wanted to talk about in this video, just sort of some of the properties of the matrices. So one of the biggest ones to remember was Hermitian. And so just remember that Hermitian means that if we have the dagger of it, which is the transpose and complex conjugate, that we just get H right back out, and that is a Hermitian matrix. And we will be using more of these ideas in future videos. And so I will see you then.